So last but not least talk of the day by Peter Müller. So Peter is a professor here at UT Zurich, working on formal verification, automated verification recently, also in network verification in the last year or so. And he's built a pretty well-known system called Whitebox for verification system applied to various domains. And now he'll talk about verification for security. So go ahead.
Okay, thank you. So this is joint work with Marco Eilers, who is in the back behind the camera, and Sam Hitz, who is not here, unfortunately. So as Martin said, we got recently interested in verifying security properties of internet routing components, in particular routers. And one of the problems that show up there is how to prove secure information flow. So that's a very well-known problem. So the problem basically is you have a program, and that program has some secret state. Say it stores, for instance, crypto keys. And you would like to make sure that an attacker that interacts with the program cannot extract any information about those secrets. It cannot learn anything about the keys, for instance, just by letting the program run and observing its outputs. So it is a very classical problem that has been studied a lot. It's typically phrased as noninterference. And here, for the purpose of the talk, we will look at the fairly simple setting. So let's just assume that we can classify all our variables into either secret, and this is typically called high, or public, that's typically called low. So we have high variables and low variables, and we would like to assume that an attacker can observe the low variables, but from observing the low variables, they should not be able to learn anything about the high variables. So more formally, this means that if you have a statement S, you can prove that it is information flow secure by showing this non-interference property. So if you have two starting states, sigma 1 and sigma 2, and they agree on all the low variables, okay? So they have different secrets, maybe different passwords, but all the low variables are the same. Then you can run the same statement twice from these two starting states, and that takes you to two different, or possibly the same, final states. And then you would like to show that the final states, again, agree on the low variables. Again, the idea is the attacker can observe those low variables, and it should not see a difference if you have these two program runs that only differed in the secret. So this is a so-called hyper property. It's a property that relates several different runs of the same program. And if you want to verify that there are different techniques, one way of doing it is to use a so-called relational program logic, like a relational OR logic, which you can do in principle, but these logics are fairly difficult to automate. So there are no like automatic verification tools available for these kinds of logics. So therefore, people are trying to follow a different approach. And one such approach is self-composition. So the idea there is basically that you would like to reduce this hyper property to a regular trace property by constructing a particular kind of program which at the same time simulates those two different runs of your original program. So basically what you do is you take your original program and you make two copies of it with consistently renamed variables. Okay? And now you just compose those programs with each other, and then one run of this new program corresponds to the two runs of the original program. Let me show you an example. Let's imagine we have a while loop, and here I use L for a low variable, so this is not a secret. So while L is less than 10, I increment L. And then if I want to prove that this is information flow secure, I would do this self-composition. I make two copies of the program. In one of them, I rename the variables consistently, here with the primes, and then I run them in sequence. And now I could easily express what it means to prove that it's information flow secure. So if I have the equality between L and L prime initially, so it's actually a low variable, it's the same in both starting states, then I need to prove that L is still equal to L prime in the final state. Okay, that corresponds to this formula that we had on the previous slide. So if you do it that way, then basically you've reduced this hyper property to a trace property, so now you can run off-the-shelf program verifiers and try to verify that program. However, if you actually want to do that, like for this particular example, then you would need loop invariants that tell you something about how these while loops manipulate L. And if you want to actually prove this for this example, you would need a very exact specification of L. So what you would need to know is precisely that if L was less than 10 initially, then it will be 10 after the loop. And if it was greater than 10 or greater equal 10 initially, then it will be the same as the original value. And only if you have such a precise specification, then you can actually verify this property. And this is an issue, right? Because first of all, we don't always want to give such precise specifications. Or if we apply inference, then typically we over-approximate, and then it's very hard to give such precise specifications. Moreover, you would have to do this not only for your local variables, but really for every memory location that is potentially modified by such a loop. So this is really not what we want. What we would rather want is a specification such as this invariant, where we just say throughout the iteration, L remains low. So throughout the iteration, I have L equals L prime. But such an invariant cannot be interpreted in a self-composed program, right? So there's basically no point here while you execute these loops where this invariant is actually true. It's true before the first while loop and after the second one. But during those iterations, it's actually never true. Okay? So interpreting such an invariant using self-composition is not possible. And similarly, if you have method calls, we would like to have method specifications that just talk about the information flow aspects. So we would like to say something like, if the parameter is low, then the result will also be low. And use that to verify a program that calls foo. But again, if you look at a call, say you have a call, A gets foo of L, then after the self-composition, you cannot use such a specification, right? Because for one individual call, this doesn't even make sense because it talks about the two runs at the same time, which you don't really see over here. So again, if you wanted to prove this, if you wanted to prove that if L is low initially, A will be low afterwards, you would need a precise specification that tells you exactly how the result depends on the value X such that you can actually figure that out. And that means that effectively you don't have modular verification. You cannot verify every procedure in isolation and reason about a call just in terms of the specification of the callee method. These problems become even more severe if you have larger programs. So here I have tiny programs, so in the self-composition, they're still very close together. So for instance, if you run an invariant inference, you still have some chance to infer a strong enough loop invariant to get the right result. But now if you compose entire programs, then these things can be very far apart and you need to compute precise results for the entire computation of the big program, which is not really what can be expected. So therefore, what people have tried is to just interweave those programs more closely. Instead of executing first the entire program once and then the entire program again, try to execute them more in lockstep. And that approach is typically called product programs. And in order to understand it, I find it easier to think of a program in terms of the control flow graph than actually the source code. So if you have this program here, if X, L gets L plus 1, we can think of it as such a program in a control flow notation. So we have a choice here. Either we take this branch, and on this branch we assume that X is actually true, and then we increment L, or we take the other branch on which we assume that X is not true. Then a product program corresponds to just composing this program with itself. So now in this visualization, it's again a control flow graph. The blue edges correspond to one execution of this program, and the green edges correspond to the second execution, right? And now you have many ways in which you could execute those two programs. Maybe you do the assume X in one program first, and then in the other one, and then you do one assignment, and then you do the other assignment. So there are many ways in which you could interleave those two programs. And on such a product program, we have now a more fine-grained interleaving, and we can, of course, specify properties about our secure information flow, about the lowness of our variables before and after the program, but we still have the same modularity issue as before. And in order to illustrate that, I would like to change the example a little bit. So let's assume we have an increment method, and let's assume we have a global variable which is supposed to be low. So I have a specification that a G is low to begin with, and G will again be low after running the increment method, okay? And then we just increment G here. So now I can change my example a little bit to say if X is true, I call increment. So instead of incrementing the variable directly, I just call a procedure instead. So now if I look at the product program again, then of course I can specify that if X is low and G is low to begin with, then G should be low again at the end. But like before, like with the self-composition, I have no good way of actually making use of such a specification, right? So it's, for instance, if you get to that point, right, this point corresponds to the situation where both programs realize that X is true, and now both want to actually execute the call, right? Then one of them will make the call first. Maybe the green one goes first, And then it gets to a state where G is not going to be equal to G prime, because G already got incremented, but G prime did not. Or maybe the blue one goes first, then G prime has been implemented, but G has not. So again, for the call itself, I don't really have a way of using this kind of specification. Only once both of them have made the call, then I'm again in a situation where my variable is actually low. So even those product programs, even though they are a step in the right direction, they don't really give us the property that we want in terms of modular reasoning, in terms of making use of such relational specifications. So what we did in this work is we defined a new kind of product program that I would like to explain to you now. So the idea basically is the following. We also construct a program that represents both runs of your original program. And in order to express which of these two runs are currently active, actually doing something, we use two Boolean ghost variables, p and p prime. So those are initially true, and they say, well, both programs want to run, but depending on how conditionals work out, they might become false along the way. And then we make all the operations of the program conditional on p and p prime. So we do that on every single procedure. So if you have this inc method as before, we would introduce these two ghost parameters to inc, p and p prime, expressing whether the first program execution we consider in our non-interference proof calls inc, and whether the second one calls inc. Okay? And so if p is true, we will increment g. If p prime is true, we will implement g prime. Okay? Then we still have this idea of a product program, but pushed further down into the procedure. Let me give you a few more examples how we encode programs this way. So more formally, I have this encoding function with the double square brackets. It takes a statement, and it takes these two variables, these two ghost variables, p and p prime, that we use for the encoding. Then for all the primitive statements, like an assignment, for instance, it's what you just saw. If p is true, that means the first program execution is active, perform s. If p prime is true, that means the second program execution is active, execute s prime. So that's straightforward. Let's look at a conditional. So if we have a conditional, there are actually 4 different cases, right? We have 2 executions, the first execution and the second execution. And for every execution, the condition could be true or false, right? That gives us 4 options in total. And basically what we do here is we compute 4 such Boolean ghost variables for those 4 situations, right? P0 says the first execution is active and the condition holds. P0 prime says the second one is active and the condition holds. And then we do the same thing for the cases the condition doesn't hold. Okay? And then we just translate the then branch with P0 and P0 prime, so the 2 cases that the condition holds, and the else branch with the other 2 variables. Okay? Now again, we've basically pushed the decision further down into the program by computing those variables and using those for the assignments. And let me show you one more case. That's the loop, and that's the most interesting case here. So assume we have a loop with a condition, an invariant j, and a body s, and again our 2 ghost variables. So here's how we do it. The key insight is that in our product program, there's only 1 loop here, right? Not like self-composition where we end up with 2 loops, or the classical product programs where we end up with 2 loops. There's only 1 loop here, okay? So what does this 1 loop do? Well, it has to iterate if either the first execution is active and its condition holds, or the second execution is active and its condition holds. Like if either of these 2 is true or both are true, you actually want to go into the loop. Okay, now we need to determine inside the loop, do we actually want to execute the loop body, yes or no? Well, we compute 2 such conditions. P0 says the first execution is active and the condition holds. P0 prime does the same for the second execution. And then we use those conditions for the translation of the loop body. And we can also automatically translate the loop invariant. It's just if the first execution is active, then the unprimed version of j is the loop invariant. And if the second is active, the primed version is the invariant. Okay? And now the point is really that we have only 1 loop here. So now, as you will see in a few minutes, we do have a way of interpreting specifications such as low of g, because there's now 1 place where we can talk about both executions at the same time. So let's do this. Let's look at relational specifications. So here's the example that we've seen before. If x holds, I want to increment g. And here you see the encoding. So the if statement gets translated into these cases here. It's a bit simpler now because we don't have an else branch. And so if P0 is true, so if we run the first execution and the condition holds, we increment G, and if P0 prime is true, we increment G prime. And now basically what you see very easily, if you know to begin with that X is low and G is low, you can straightforwardly prove that G will be low afterwards. Right? So if you branch on something that is not a secret, you know that you preserve the lowness of G. But if X might be a secret, so you don't know that X is equal to X prime, then those two could be different, and then you might execute only one of the two increments, and then you could not prove this anymore. So now let's go to the case with the method call, because this is where we had trouble before. So now again, I replace this by just calling inc here, like before. So then this is my encoding. I compute these two conditions, and then instead of branching right away, I just push these conditions into the inc method by passing them as parameters. And here's the inc method itself. It just increments G. And here's the encoding. We have these two condition ghost variables here, and then the increments are conditional. Okay? So now if you wanted to verify this client, of course, we wouldn't succeed because we want to do modular verification. We want to use only the specification of inc, but inc doesn't have a specification. But now the point is we can actually use such a relational specification now. So we can say inc requires G to be low to begin with and guarantees that G will remain low. So if we encode that, here's how the semantics of low is defined. Low means that if both executions get there, so you have P and P prime, then the variables must be the same. Right? This is what you would expect. That's what lowness means. This is just necessary because if the execution doesn't even get there, then the value of G or G prime doesn't even have a meaning. Right? It's completely meaningless to talk about the variable of an execution that is not active in that sense. So this is where this implication comes from. Okay, now you can first of all easily see that we can verify this method. Right? If you can assume this, you can easily prove that. That's a totally straightforward proof. And we can also easily verify this example over here, right? Because this specification is strong enough to tell us that if X is low to begin with, we can actually prove this property. So now we did use a relational specification. We don't need to know what inc does functionally, right? We don't use the fact that it's actually an increment. So this could be an abstract method. This could be a super complicated method that we cannot easily specify. It just doesn't matter, right? Because we have a much more abstract way of specifying the behavior. So that's the basic idea. So with this idea, we can do non-interference proofs. And what I would like to do in the remaining couple of minutes, I would like to show you that this idea is actually powerful and expressive enough to also include a couple of interesting twists that are useful when you do secure information flow proofs. So, yeah.
So are you doing verification on the white boxes at all?
No, so the white boxes is... Right, so the white box is the source program, right? And the specifications there is what we expect from the user. The pink boxes is what our translation generates, and this is what we would verify.
Okay, and is there a reason not to try? So I guess I'm wondering why not just do verification on the white boxes and then prove one meta theorem once and for all, which says that verification implies the non-interference.
Well, the thing is that what you want to prove on the white box is a property of two program executions, right?
Yeah, but I'm wondering whether that could just be derived as a meta theorem, as a consequence of, like, let's say you have a logic that allows you to prove the reason directly about the low predicate.
Yeah. So
then just prove a
so
implying that.
Yeah, so I guess that might be possible. The reason we do it this way is because this is how we automate the entire thing, right? So this pink thing is the kind of input that a state-of-the-art verifier understands. Take Viper or Boogie or any tool like that, right? So if you generate a program like that, then from an implementation perspective, you're done. Right? But from a theoretical perspective, yes, we might want to lift this up again to the white level and show a theory there. All right, so let me show you some of the twists. So here's another example. Let's imagine we have a print function. So print something on the screen. And so naturally, we would expect that the parameter must be low. You should not just print your secrets on the screen. But that turns out to be not enough. So imagine, well, the translation is straightforward. Imagine that you have a program that iterates for a while, and in every iteration prints 5. Okay? So now if y happens to be a secret, then depending on the secret, you will have more or less views printed on the screen. So you do leak information. So even though you print something very uninteresting, just a constant, you still leak information just by the number of print statements that you execute. And what that shows is that the technique that I've developed so far cannot really handle that. So here's the encoding of the loop. And the interesting part is the call to print, right? But the precondition of print just says if both conditions are true, they, x and x prime must be the same, but x and x prime, these is the constant 5, so they will always be the same. So this would clearly verify, but it's a leak, right? It's not a program that we would like to verify. So what this shows is that for print, it's not enough to show that what we print is a secret. It's a secret that we print at all. And so we can encode that by having a special kind of condition which we call low event. And by low event, we mean it's an event that an attacker can observe. So either both program executions should do it or none of them. So we can therefore encode it very easily. It just means that P is equal to P prime. Either both do it or none of them do it. Okay? And now with this kind of specification, we could not verify this anymore, right? Because if Y might be a secret, we don't know that P and P0, that P0 and P0 prime are the same, so the precondition check would fail here. So you would need a stronger specification. So first of all, you would need to specify in your loop invariant that actually you are in a situation where both control flows reach that point. There are no conditionals high up that already prevent one of the programs to get there, which we can translate here. But then since this depends on whether Y is a secret or not, we will also have to say that Y is not a secret. Y is low. And once we translate that as well, so now we are done, because if we know that Y and Y prime are the same, that means those two conditions will give us the same value, and then we actually live up to this precondition over here, and now the program verifies. But it only verifies under the assumption here that Y is low. If Y wasn't low, it would fail as it should. Another thing that is really important in secure information flow is declassification. So typically your computation does depend on the secrets somehow, and you want to be able to use the secrets in some form. So the most standard way of doing that, for instance, is to check whether a user gave you the right kind of password. So here's the situation. Imagine we have an equals method on strings, and the specification says if the input strings are low, then the result is going to be low as well. Okay? And now we have a program that compares a stored password to a user input, and depending on whether the two are the same, you either proceed with the computation or just say, sorry, incorrect password. So obviously this leaks information, right? And verification would fail, but we write such programs and we would like to be able to say, well, that's okay, leaking this one bit, whether the passwords are the same or not, that's okay. And that's what we typically do by declassification, and we can do that very easily just by providing a declassify statement, saying that we would like to assume that whatever the condition is here, that condition is actually low. And so the translation is completely straightforward. It's just assuming in the encoding that if both executions get there, they will have the same value. So the reason why we can do this is, the reason why this is sound is that in our encoding, you never know that something is definitely not low. Right? If you could ever figure out something is definitely not low, then here you could introduce a contradiction and it would be unsound. But you will never know that. Either you know that something is low or you know nothing. Right? And if you know nothing, then the verifier will always make a worst case assumption and at least consider the case that it might be high, but it never knows for sure that it's high. So this will never lead to unsoundness because it can never lead to a contradiction. How much time do I have? You're just a mean person, Martin. Okay, so let me what slide is that? 12. Okay, I can make this in 2 minutes. So another interesting case is termination, right? So typically an observer, an attacker, can also observe whether or not a program terminates. That's something that you see by just running it. So it's a good idea to make secure information flow analysis termination sensitive, to say that termination should not depend on any secrets. So we can do that very easily. So here's an example that shows the need for that. If Y might be a secret, right, then the termination of this program, of course, depends on the value of Y. So you learn something by running it and observing whether the program terminates or not. So the way we can handle this is as follows. We require from our programmer a specification that is a precise condition that tells us whether or not the loop is going to terminate. So by precise, I mean an if and only if condition. Okay? So this loop terminates if and only if y is greater equals 0 to begin with. Okay? And once we have that, we can basically verify that for every loop, that the two executions that we look at either both terminate or both run forever. But you cannot extract information by seeing that one does and one doesn't. And the encoding is a bit more involved. I will not go into the details here, but the idea is basically that there are two main things here that are interesting. So the first thing is, at the beginning, we just record in this local variable t whether or not the loop is supposed to terminate. So if t is true, it must terminate. If t is false, it must not terminate, right? And then one of the key assertions is the first one here. So this one looks a bit confusing, but it's actually very intuitive. So if p and p prime have the same value, then it's straightforward, right? If p and p prime, for instance, are both true, that just means they must both terminate or both not terminate. If they're both false, that means we don't ever execute this loop anyway here. We don't need to bother at all, so that's just fine. The interesting case is if one is true and one is false. Let's assume p is true and p prime is false. That means the second execution doesn't even get there. The second execution doesn't execute that loop. And therefore, we want the first execution to definitely terminate, right? Otherwise, you would have one execution that terminates because it doesn't even execute the loop, and the other execution runs forever. And this assertion makes sure that's the case. And then the remaining assertions, the loop invariant just makes sure that if you are supposed to not terminate, the loop condition remains true all the time, so you will definitely not terminate. And these conditions here are just the usual termination conditions. If you are supposed to terminate, then you need to reduce some variant function that we also assume the programmer has given us. So let me wrap up. I think what we have here is the first modular technique for verifying secure information flow using existing verification technology, and that means verification tools out there. The idea behind it is that we have a new form of product programs that interleaves the executions of these two executions of the program very closely, such that we can give an interpretation to relational specifications. We have implemented that in Viper. Viper is a fairly powerful program logic, similar to separation logic, so we can easily handle heap data structures, database-free concurrency, and all these things. So this technique generalizes nicely to these things. And it is not limited to secure information flow. In fact, you can, in a rather straightforward way, generalize that to arbitrary k-safety properties. So you can also look at k copies of the same program and then prove other properties, such as, for instance, determinism or checking read effects of programs and things like that. And with that, I conclude.
Questions? Yes.
So this reminds me of a work by Aaron's group where they were checking if two programs do the same thing. One thing that they observed there was that if a single program would be verified, say, by interval domain, then the program then the comparison would need some more powerful domain like relational domain. So do you observe such kind of effects that you need more powerful domains here to prove the thing than the original program?
So far, we've only looked at situations where the specifications were given by the programmer, right? So far, we're not inferring anything. But all the examples that I've seen so far only have specifications of the forms that you have seen here. So you have the p and p prime implies some equality. So it's a very limited form of properties we need. So I'm very hopeful that we can develop a proper inference for that, and have not seen the need for any advanced domains as you described. But what Aaron did is more difficult, right? Because we only look at n or k copies of the same program, whereas he compared two different programs. So that's a more difficult problem to solve.
More questions? So, I mean, it's very nice that you're using off-the-shelf verification tools, but how does this compare to specialized tools like Joanna, for instance, for information flow?
So Triana is a static analysis, right? That means it's just more approximative. So, I mean, we basically have the full power of a verifier. We can reason very precisely about the values, for instance, that our variables have. So you can easily come up with examples where Triana cannot prove information flow security, and we can. This is not difficult. If the question is, do such examples show up in realistic programs? I can't tell you yet. It's very easy to write down artificial examples, right? But it's just like always, right? The experience just shows that static analysis goes a long way, but typically you always end up with also like difficult cases where you need to know, where you need to precisely reason about the semantics, and they just cannot there.
So it seems the most difficult specification you require is the termination specification and the ranking functions.
Yeah.
If you had an analysis that knew how to infer those properties, you wouldn't even need to check what you explained at the end, right? If you believe that the ranking function is correct, I guess you don't even need the assertions. You can just use this as the way of defining your T's and you're done. Is that right?
Right. The ranking function alone is not enough, right? We need really an if and only if condition. You also need to know for sure that sometimes you don't terminate. So a termination analysis typically doesn't do that.
Ah, okay.
Right? It just says, I didn't find the ranking function. But then, so we really need this if and only if.
I see, yeah.
Okay, no more questions. So let's thank Peter.